All right, time for us to do some practice with problems which involve derivatives of inverses as well as logarithmic differentiation. As always, make sure you're doing it lots of practice. The more you do, the better you're going to be. We know you're great, but we know you can even be greater. So keep doing that work. When you're watching these videos, make use of that pause button. Follow along, and when you get to a point where you're like, I think I know what to do next, pause and see, I see it. I see it. Start making the connections. Start becoming powerful. And of course, with great power comes great responsibility. All right, let's begin. So, suppose that h of x is a product, f of x times g of x, and we know it's an invertible differentiable function. And further, suppose that we know the following information. So we have a lot of information about f, its derivative, g, and its derivative at various places. And we're asked to answer the question, what's the tangent line to the curve y equals h inverse of x at x equals 12? All right, good. So, let's think about this. So we need a tangent line. Of course, that means we better be thinking about a point. And if we want a point, that would be the point 12, comma, h inverse of 12. And we need a slope. Well, that would be the derivative of h inverse of x evaluated at 12. Okay, good. I will say it's kind of tricky to write the derivative of h inverse because sometimes the prime looks a lot like a 1, so it can be a little bit confusing. So this is a way for us to say the derivative at 12. Okay, well, probably we should focus on the point because we do need to know what's happening with h inverse of 12. Now, I can't help but notice they did put a 12 here. I think they're trying to trick us because that seems too easy. Let's be careful here. What does it mean to find h inverse of 12? Well, what it means is we're really looking for some x where h of x, which is the f of x times g of x, produces a value of 12. So we start looking and we say, okay, well, let's start with 1. So that would be 2 times 5. Well, that's 10. No. Next at 2, 3 times 4. Yeah, it works. 12. Good. Now, just for sanity's sake, let's just check the rest. 6 times 3, that's 18. 12 times 2, 24. 13 times 2 is 26. So, where do we see it? Lo and behold, this is where we really need to be focusing our energy at. Because we see that f of 2 times g of 2 is equal to 12. So we come to the conclusion that tells us that h inverse of 12 is 2. And that really, why do they give us so much of their information? Just so that we can test, all right, do we really understand where we need to look? See, sometimes they give us more than what we actually need. So we may not use the whole set of entries, the whole data, if you will. All right, good. Well, we have our point. Next up, our slope. So, according to the rules for derivatives, what would this be? Well, we would say it's 1 over h prime at h inverse of x and evaluated at x equals 12, which really means 1 over h prime of h inverse of 12. Now, because we did h inverse of 12 already, we know that h inverse of 12 equals 2, so this is 1 over h prime of 2. Okay, so now our next thing we need to do is figure out, well, what is h prime of 2? Well, we know that h of x is f of x times g of x, because that's what we were told about h of x. So h prime of x, product rule, 3 to the first, times the second, plus the first, times the derivative of the second. All right, and therefore, h prime of 2 would be f prime of 2 times g of 2 plus f of 2 times g prime of 2. So we start reading stuff off. So f prime of 2 is 2. G of 2 is 4. Then we have f of 2, which is 3. And g prime of 2, which is negative 2. So we get 8 minus 6, which is 2. Okay. Now, of course, that 2 is different from that 2, but sometimes it happens that we get the same numbers. There's only so many numbers, so oftentimes numbers show up in multiple cases. That's perfectly fine. So, what's our point? Well, our point is 12, 2. Our slope, we just worked it out as 2. Oh, wait, no. Careful, not 2. See, that's h prime of 2. Our slope is 1 over 2, right? Because it's 1 over h prime of 2. There we go. That's right. So our line would be y minus our y value, 2, is equal to our slope, 1/2, x minus our x value, 12. Now we can clean this up. So, for example, multiply the half through, because that's an easy number to work with. So we could say y equals 1/2 x. A half times minus 12 is minus 6. Add 2 more, that would make it minus 4. And there you go. That's the answer. 1/2 x minus 4. Good. Nice. Fun problem. All right. Let's try another problem. Okay. So, here's our function. F of x. 2x to the 5th plus 3x plus 1. And g of x is f inverse of x. Find g prime of 6. Okay. Wow. Okay. Wow. Now, we should think about a couple of things. Now, you might think, hey, f inverse of x, is that equal to x? No. Just because you take the inverse function and plug it back into the inverse function doesn't mean that you're undoing the inverse. And so it's not the case that f inverse of x is equal to x. That's not true. Okay. Well, maybe we can find f inverse of x. No, don't go that way. It's not going to be very productive. Because if we wanted to go that way, we'd have to solve what's called a quintic. That's a very fancy way of saying 5th degree polynomial. And some quintics can be solved, but a lot can't. And it's just, we would probably not make any progress. So this is a case where we couldn't find the inverse. At least we certainly couldn't find it very easily. So, what do we do? Well, the good news is we don't have to find the inverse because we're not after an inverse. In fact, what we're after is a number, which is good news for us. So we have our rules, so we just need to remember our rules. So what's our rule? Well, sort of our big rule for right now is how you take the derivative of an inverse. What's the clue that we need to know about the derivative of the inverse? Probably because we see that there's a derivative and the function involves an inverse. So see how easy it is to pick up on these patterns? Now here it's kind of obvious, but if you can learn to spot patterns and say, okay, I see, it's like, oh, here's when I take a derivative of an inverse. Here's where I use logarithmic differentiation. Learning to spot these things is useful because once you remove context and you're out in the wild, you're not going to be so clear. Like, wait, what rule do I use? But if you've been practicing on pattern finding, pattern matching, you'll be in good shape. All right, so let's write down our general rule. So I'm going to write it as h, just so we have context. So if I have the derivative of some function, I'll call it h inverse of x. The rule says it's 1 over h prime of h inverse of x. Okay, so here we go. We want to find the derivative g prime of x. So let's think about that. that says we want to take the derivative of f inverse of f inverse of x, because, well, that's what g of x is. See, g of x is f inverse of x. Now, here's where we want to be careful, because it's easy to get lost in the weeds if we're not paying attention. So let's come back up here. We see here that we're going to need a chain rule because it's a function f inverse inside of another function. So I just want to be really clear of how to read this. So when I'm thinking of function to function with the inverse, this x is the inside function, and that is what you would put into here. Okay, so if this is the inside, you put whatever you would put here goes into that slot there. So let's follow it through carefully. This would be, here it's f instead of h, but 1 over f prime of f inverse of, now, see, 1 over h prime h inverse of, and now it's whatever's on the inside. In our case, our inside is this f inverse of x. See, that's what's on our inside. So that's what's going to go into there. So that's going to be f inverse of x times, by the chain rule, the derivative of the inside. So that also is what's going to go into there. So the derivative of f inverse of x. Okay, so one more round. So this is 1 over f prime, whoops, that's prime, of f inverse of x times, now the derivative of f inverse of x is 1 over f prime of f inverse of x. Okay, and good. Now we've taken the derivative. So what comes next? Well, the next thing is to plug in 6, because we want the derivative at 6. So we can say g prime of 6 is equal to 1 over f prime of f inverse of 6 times 1 over f prime of f inverse of 6. So we need a couple of things for context. First off, let's make some notes. What is f prime of x? Well, we can take that derivative pretty straightforward. 10x to the 4th, because the 5 comes down, 1 less power, plus 3. Now, let's also think about what do we need? Well, we need to know f inverse of 6. So to figure that out, we take our function, 2x to the 5th plus 3x plus 1, and we set it equal to 6. Now, is there a value for x that solves this? Well, yeah, there will be, because the problem asks us. Is there a good one we can guess? Well, if we're good at guessing, and we'll get better as we do more of it, can you see a good guess? Yeah, right. X equals 1. So, see, x equals 1 works. So, what does that tell us? Well, what it tells us is that f inverse of 6 equals 1. All right. So, now we know what f inverse of 6 is. So, that says this is 1, and it says this is 1. Now, hold on, we're not done with the inverse yet. Notice, what do we have here? We have f inverse of 1. So now we have to do another problem like this. Okay, so now we have another one. All right, when does 2x to the 5th plus 3x plus 1 equal 1? Do we see a nice value for x? Because that's finding f inverse of 1. I see a really good one. Okay, namely 0. See, yeah, 0 and 1. Those are your two go-to. X equals 0. It works. So what does that say? It says f inverse of 1 is 0. All right? So there we go. Good. So now we can say, aha, this is really 0. So what we now have is this 1 over f prime of 0 times 1 over f prime of 1. Well, we can compute those numbers. If we plug 0 into the derivative, we get 3 because the first term goes away. So this is 1 over 3. If we plug 1 into the derivative, we get 10 plus 3, which is 13, times 1 over 13, excuse me. And 3 times 13 gets us to 39. So 1/39. There you go. That's the derivative of g at 6, 1/39. Cool. Yeah, see, we can handle these nested things. You just got to be careful and think about, okay, what's the current layer? Work your onion. Be careful. Be careful. And with practice, it'll come naturally. You'll just understand how to be careful. And you'll stop making the really silly mistakes. You'll never stop making mistakes completely, but you'll stop making the really silly mistakes. Okay. Another problem. Find the derivative of x cubed plus x, sine of x to the x squared, divided by secant of x, square root of x squared plus 4. All right, can we see what rule we need to use here? It's logarithmic differentiation. We don't have a choice. We don't have a choice. Now, why don't we have a choice? Well, it's this piece here, this sine of x to the power x squared. That just says you got no choice at all. Now, what's so bad about sine of x to the x squared? Well, you have a sine of x downstairs and an x squared upstairs, because you have x, that variable, showing up in both the upstairs and downstairs pieces. It's in both places. We don't have a way to handle that directly. So what we can do is, by using logarithmic tools, we can pull things down, and therefore we can handle them. So that's why we want to say, okay, let's use our tools to help do this. So logarithmic differentiation. Now remember, when we're doing logarithmic differentiation, the main bulk of the work is really applying the rules for logarithms to pull things apart. So anticipate not doing much differentiation until the very end. So here we go. So the rules for logarithmic differentiation, we'll write down here to the side just as a reference. So the derivative of f of x is, you write the function down again, and then you times it by the derivative of the natural log of the function. Now, I will say there are other ways to do logarithmic differentiation that use sort of the notion of implicit functions. You set y equal to your function, you take the log of both sides, and you do various things. I prefer this method because it's more versatile, and you don't have to sort of come up with this extra layer of complication. It just can be built right into what you're doing. All right, so here we go. So this derivative is equal to, you write your function again, x cubed plus x, and then you can write all out sine of x to the x squared. I will say probably the hardest part about this function is just being very patient, because you have to be patient, and there's a lot of writing involved. All right, so the function again, that's my f of x times the derivative of the log of the function again. Okay, x cubed plus x, sine of x to the power x squared, all that divided by secant of x times the square root of x squared plus 4. All right, good. Whew. Done. We did it. Okay, now what? Well, the next thing is, we're not taking derivatives yet. Now we're going to start pulling things apart. What do we mean by that? Well, wherever we have terms upstairs multiplying, that's going to become addition. Terms downstairs, again, they could be multiplying, or there could just be one term, but upstairs we add, the downstairs we subtract. So we still have that term in front. We're not going to forget it. And so we still write it down. Sine of x all to the power x squared. Divide that by secant of x. Square root of x squared plus 4. Then, we still haven't taken a derivative yet. We're still in our use properties of log mindset. log of x cubed plus x plus log of sine of x to the power x squared minus log of secant x minus log of square root x squared plus 4. All right, so as I said, the upstairs terms get added, the downstairs terms get subtracted. All right, good. We're making progress here. Now, that's our sort of pull apart. We also have the ability to pull exponents down. Now, we have a couple of exponents. You might say, okay, here's an obvious one, x squared. All right, that can come down. Do you see another one? Back here, right? Because what do you have? You really have x squared plus 4 to the 1/2. Now this 1/2 can come down. Do you see another one? You might be tempted to say, hey, how about the 3? Can the 3 come down? No. Well, why not? That doesn't seem fair. We were doing lots of pull down exponents before. The problem is the plus. Log does not get along well with addition. So if you see a plus showing up, it basically says, okay, can't go any further. So when you get down to log, there's a plus on the inside. It's like, nah, that's it. Can't do anything. In other words, we can't do like, oh, pull the exponent down off of just that term. No, can't do it. Now, you could do the following. We're not going to, but I just want to point something else out that you could do. You could say x cubed plus x is the same as x times x squared plus 1, and then you could keep pulling apart even more. But at this point, I don't think we really gain much by doing that. Now, why do I say you don't gain much? What have we gained? Because it looks like what we had is originally we're taking the derivative of just one thing, and now, because we have all these things being added and subtracted, now we have to take the derivative of like 4 things. But here's the key. See, the derivative of the one thing was like one really really big crazy thing. And now the derivative of the 4 things are like, well, these are all not so bad. So our trade-off was, yeah, we have to take more derivatives, but they're a lot easier. And therefore the total amount of work is much more straightforward. It's easier to finish the problem. So now let's rewrite it one last time, just so we catch up with what we've done, and then we'll take our derivative. All right. So, like I said, one of the hardest parts about these types of problems is you have to keep rewriting and rewriting. We still haven't taken derivative, so we got to keep that derivative there. Remember, don't forget, notation is important. And if you lose your notation, well, you might forget what you were doing, and then all sorts of things could happen. So here we go. Now you might wonder, do I really have to bring this half down? And the answer is no. But you should always, if you can bring exponents down, you should, because it will become a lot simpler. Taking the derivative of x squared plus 4 is a lot simpler than taking the derivative of square root of x squared plus 4. So we're now ready to write down our answer. And depending upon how much we feel like simplifying, this is the final step or the penultimate step, which means the step before the final step. I don't feel like simplifying. I feel like I've written down enough. So we'll make this the final step. So the nice thing about taking derivatives of logs is it's really easy. It's 1 over what's on the inside, so x cubed plus x, and then you multiply by the derivative of the inside, which really means you just write the derivative upstairs. So the derivative of x cubed is 3x squared plus derivative of x is 1. Here we have a product, so we take the first, usually I do the derivative of the first times the second plus the first times the derivative of the second. So the derivative of log sine x, the sine x goes downstairs, derivative of sine is cosine. So it becomes cosine x over sine x. Minus, log secant, so the secant goes downstairs. The top is the derivative of secant, which is secant tangent. And then we have minus a half, and then log of x squared plus 4, and the derivative of that, x squared plus 4 goes downstairs, and the derivative of x squared plus 4 is 2x. That's what goes upstairs. All right, now, could we simplify some more? Oh, yeah, sure we could. So we can do things such as the secant of x cancels, a 2 cancels, and if we were in the mood, we could say cosine x over sine x becomes cotangent x, which is cosine over sine. But those are all just sort of, doesn't really change anything. It just expresses it in a slightly easier way. But that's how you take the derivative. There you go. There it is. In all its splendor. So it's amazing. It's kind of a very long expression. But I think it's certainly a lot better than if we tried to do a quotient rule. Could you imagine doing a quotient rule with that? Oh my goodness. We would need like 5 or 6 pages because it would take us a while. But we don't need to take a while. We've got better tools. Use the tools that you have. Make life better for yourself. All right, well, that's a good problem. All right, one more problem. Here we go. So, let f of x equal x to the fifth plus 2x plus 1. And find the tangent line to, oh my goodness, y is equal to x cubed of f inverse of 4e to the power 2x minus 2 plus 12 f inverse of x at x equals 1. All right, well, let's get into it. Let's get into it. So for convenience, let's give this whole expression here a name, g of x. All right, so what do we need? Well, we need our point, which would be at 1 comma g of 1. And we need our slope, which would be g prime of 1. All right, well, let's start with g of 1. So what do we have? Well, g of 1 is, according to this, 1 cubed f inverse of 4e to the 2 minus 2 plus 12 f inverse of 1. Okay, so we're going to start sort of peeling through here. F inverse of 1. So that says, look at your function f. X to the fifth plus 2x plus 1. When does it equal 1? Well, that's not so hard to figure out. We just need to find any value that works. 0 works, and so the fact that 0 works, that tells us that f inverse of 1 is 0. So that's 0. Hey, great news for us. We now know what this is. That's going to be 0. So, that part's going to go away. Then we have e to the 0, which is 1 times 4. So that's 4. And then 1 cubed is 1. And so what we really have is f inverse of 4. So, well, what does that tell us? Well, that tells us we want to find some place where x to the fifth plus 2x plus 1 equals 4. Okay, well, can we think of a good choice? And, well, I think you can see a good choice. X equals 1. Now, you're probably thinking, is it always going to be 0 and 1? Not always, but you should anticipate it should be a relatively nice number to work with. So think about what are nice numbers to work with. Or look at your expression. Maybe you have something interesting, like you may have like e to the power x minus 2. It's like, oh, hey, what makes x minus 2 a nice thing? Well, 2 would. Okay, maybe that's a nice thing. So just sort of going, it's all about context. So what do we have? We have that f inverse of 4 is equal to 1. And so we have that g of 1 is 1. So our point, 1 comma 1. All right, we're halfway there. We have our point. Of course, the other half is the more interesting half. We need our slope. All right, so how are we going to do that? Well, we need to tackle g prime. So let's do that. So So what do we have? Well, we're going to need to do product rule. So we're going to take the derivative of the first, which is 3x squared, times the second, f inverse 4e to the 2x minus 2, plus 12 f inverse of x. Okay, so derivative of the first times the second, plus, I'm going to run out of space, so I'm just going to go to the next line. The first, which is x cubed, times the derivative of the second. Now, let's work through this, take our time. No need to rush. Let's savor this. Like a nice, good quality tea. Just enjoy it. So, derivative of f inverse. All right, so the way we do that is we take 1 over f prime of f inverse of, and then whatever's on the inside. So what's on the inside? That whole expression. So 4e to the power 2x minus 2 plus 12 f inverse of x. Okay, good, right? And there we go. Are we done? No. What else do we need? Now we have to multiply by the derivative of the inside. What's the inside? It's this thing right here. Okay, so that's going to be multiplied by, all right, so we have a plus, which means we do the derivative of each part and add. So here we have 4. We take the derivative of e to the power 2x minus 2. Well, that's e to the 2x minus 2. And then we're going to multiply by the derivative of 2x minus 2, which is a 2. So that comes down, giving us 8 e to the power 2x minus 2. Okay, plus 12. Now we need the derivative of f inverse of x. Well, that is 1 over f prime of f inverse of x. Okay, we made it. We made it. Just barely, but hey, that counts as long as we made it. Now, where do we go next? Next, we're going to plug in 1 because we need g prime of 1. So let's plug in 1. So g prime of 1 is 3 times 1 squared, so that'll be 3 f inverse of. Now, we've plugged 1 in here before. F inverse of 1 we said is 0, so that term went away, and then we got e to the 0, which was 1 times 4, so it's 3 f inverse of 4 plus 1 cubed, so that'll be 1. So then we have 1 over f prime of f inverse of this. Well, we know what that is. That's f inverse of 4. We just worked through that. That's the same as what you saw up here. And then that's multiplied. Here we have 8 e to the 0, so that's 8 plus 12 times 1 over f prime of f inverse of 1. Okay, so to make more progress, we really need to figure out what's happening with f prime. So we know what f is, so let's make some notes here. F prime of x is 5x to the 4th plus 2. So let's be careful here. All right, for this term, f inverse of 1 is 0. We know that because we did it over here. See, f inverse of 1 equals 0. So this is 0. So f prime of 0 is what? F prime of 0 is 2. So this whole piece here becomes a half. So 1 half, then there's a times 12, which means you get 6 plus 8, which means this big thing on the end will become 14. All right, good to know. On the other hand, what do we have? Well, we have 1 over f prime of f inverse of 4. We know f inverse of 4 is 1, so this part right here is 1. So what do we have? Well, it's 1 over f prime of 1. F prime of 1 is 7. See, 5 plus 2. So this part is a 1/7. So we have 1/7 times 14, which means this whole last term becomes 2. Oh, wow. That's pretty simple. here, f inverse of 4, well, we know that's 1. So we have 3 times 1 plus 2, which tells us that, lo and behold, that g prime of 1 is equal to 5. All right, nice, nice. It's like they wanted it to work out to a beautiful quantity, because now we know our slope, it's 5, and we have our point, 1, 1, and therefore we put it all together, and we can say that y minus our y coordinate is equal to our slope, 5, x minus our x coordinate, or if you like, y equals 5 times x. See, this would be a minus 5 plus 1, which would be 5 times x minus 4. And there we go. That's the answer. That was a lot nicer than we probably thought it was going to be when we looked at it initially, because there was just all this stuff going on. But of course, once you worked it out, it's like, oh, hey, things simplify. The problem becomes beautiful. And that's like math. Math is beautiful, and life is beautiful. All right. Well, keep staying beautiful, my friends. Hope you have a great day.